This is the video lecture for round and rolling things and the direction of the force of friction. This is chapter 17, general plane motion. And these principles are used extensively at the end of chapter 17 as well as in 18 and 19. So we'll be visiting these concepts every day for the next couple weeks. The in-class lecture was fairly interactive. I had some demos, and so I'm not going to try to recreate that in-class experience. What I'm going to try to do is just kind of give you the highlights here, point out the main processes, and you can follow the notes here. You can do a print screen and print these things if you need to go through them more carefully, but I'm not going to try to read every word. I'm just going to give you the highlights. But the main thing about finding the direction of the force of friction, at least in the way I think anyway, is to imagine what the behavior would look like if there was no friction. For example, if you cast this round thing onto a frictionless surface, or maybe just threw it out in space in the air, and if it wasn't spinning, then it'd have no reason to spin. It would just translate. However, if you throw it onto a surface, we know from observation that it may slip for a moment, but very soon it rolls without slipping, and it just rolls along. Well, the rolling has an omega, and the only way for that omega to begin to happen is if there's a force of friction causing it. So if it rolls in the counterclockwise or in the clockwise direction like this, then the force of friction has to be going in this direction to cause that clockwise moment or clockwise rotation as it rolls to the right. So anyway, that's kind of the key concept, is the direction of the force of friction causes the omega in virtually all of our situations here. So the force of friction opposes motion. If a box is sliding uphill, or if it's sliding downhill, force of friction is going to oppose it. The same thing if a round thing is rolling uphill. If it rolls without slipping uphill, then the force of friction has to be causing that rotation. And then if it changes direction and starts rolling downhill, then the force of friction also changes direction and causes the rotation going in the other direction. If you're pulling the disc or the round thing from the middle, then you have the same kind of behavior. Again, if it was out in space, it would just go forward like that. But the force of friction is what causes this omega to happen in the clockwise direction in that way. A couple of things that are kind of odd is when we pull from the bottom, and I demoed this in class, but if we pull from the bottom, it may feel like it should rotate backwards, but it actually does rotate going in this direction, and the movement goes in that way. So velocity goes that way. To keep it from spinning backwards, the force of friction has to go in this direction. If I pull straight up, it goes in that direction. If I pull straight down, it moves in that direction. And so the only thing causing those motions, those velocities, are going to be forces of friction. So you can see the directions they go. All right, so the last thing here I want to mention here is that if I pull from the bottom or from the middle or the bottom, the force of friction goes to the left. However, if I pull from the top, force of friction goes in this direction. And that suggests that there's a change someplace in the middle here, between here and here, where the force of friction changes direction. And that's what I want to talk about here. And this page gives you the kind of the process for developing where the transition point where the force of friction goes to zero, or where the force of friction changes direction. And at the point where it changes direction, the force of friction actually becomes zero. So when I set up my two equations, my force equation, my moment equation, I can put set the force of friction equal to zero here, and then I can solve for d, the distance from the bottom, wherever the force is applied in my spool, then I can find d, where the force of friction goes to zero, and that's the transition point. Now the curious thing about that is that if at the point where the force of friction is equal to zero, the force P has fallen out of the equation someplace. It cancels out here, or it's substituted, so that D is not dependent on the force of is not dependent on either the force of friction or P. so that it doesn't matter how hard you pull, you can never make it slip. So that's kind of a curious thing. No matter how hard you pull, you can't make it slip. All right, now how do I determine the direction of the force of friction? Well, again, if I set up my roller like this, and with a distance d from the bottom, we're going to assume the not slip condition to start with. And in the not slipping condition, we're going to say that the force of friction does not equal mu normal, but A does equal R alpha. And this is back from chapter 17 stuff, or 16, I guess. And what we're going to do to resolve the actual direction of the force of friction is we're going to draw it as a positive and then find out the value of it and find out whether it was drawn as positive correctly or drawn as a positive incorrectly. So you can follow my equations here, but if I do my two equations, some of the forces in the x is mass times acceleration in the x, and some of the moment about A is equal to IA alpha. Now again, I can use A down here as my point of reference easily. I could have done some of the moments about G as well, but here I can solve some of the moments about A's IA alpha and use the parallel axis theorem. But at any rate, using these two equations, I can resolve force of friction, and then I can say that if I find out the value of the force of friction is equal to a positive, then obviously I drew my arrow correctly, and if I found it was a negative, then I drew my arrow incorrectly, and that can help you actually nail the direction of the force of friction. Along with that, though, you still have to check for slipping, and when you check for slipping, what you do is you compare the actual force of friction that you've resolved, and you compare it to the maximum that it can be. And you know the force of friction cannot be greater than mu normal. So that if the force of friction is less than mu normal, then not slip condition is confirmed and you're okay. However, if the force of friction that you find here is greater than mu normal, that means it's slipping, and then you have to start all over again, and none of your answers are valid anymore. You have to start over with not slip assumptions. Recall here that I started with you have to start over with slipping assumptions. I started this piece with a not slip assumption. All right. Now, does the force of friction direction change as it moves through not slip to slip? For example, let's say that we're pulling up here and we're in a not slip condition, but you can probably guess that if I pull hard enough, it would slip. And then which direction is the force of friction going there? Well, I think you can probably follow my logic here, but there's nothing to cause the force of friction to change direction. Therefore, the force of friction is the same for both slipping and not slipping conditions. In other words, force of friction is going to stay consistent through the transition between not slipping and slipping. And so a key takeaway here is that once you find the force of friction, you're safe in assuming that it's going to be in that same direction for both slipping and not slipping conditions. All right, let's talk about slipping just a little bit. This page can help you understand, I hope, the slipping concept. But when an object is not slipping, we know that A equals R alpha. However, when it begins to slip, A equals R of alpha does not apply anymore. However, the force of friction does equal mu normal when it's slipping. So here is my slipping conditions, which are slightly different than the not slipping conditions. Under slipping conditions, force of friction is equal to mu normal, but A does not equal R alpha anymore, and this applies to all round rolling configurations. And then you may sometimes find it handy to calculate the mu that it takes to, the minimum mu to prevent slipping. So I'll just let you read this, but if it's not slipping, it's because there's enough friction to keep it from slipping. However, there's a transition point where it has just enough friction to prevent slip. And at that unique spot, the force of friction is equal to mu normal and A equals R alpha. Now these two relationships are only applies at the unique spot, at the one point, or the one value of mu to prevent slip. Minimum mu to prevent slip. Okay, this is an example problem which is fairly easy, but let me just talk you through it real quickly. let's say we're pulling this roller with a force of 200 newtons. It weighs 100 kilograms. We're given in the problem that it's a not slip condition, or it's not slipping, and we want to find the force of friction, A, and alpha. Again, our not slipping condition says that force of friction does not equal mu normal, but A does equal our alpha. Our two equations are right there. Sum of the forces in the x is mass times acceleration in the x. And I'm using here some of the moments about g as Ig alpha. And what you'll find is I will use the moment equation, kind of mix them up. Sometimes I'll sum moments about g, sometimes I'll sum moments about a. And you may find one may work a little bit better for your circumstance depending on how you approach the problem. But what we'll find here is a two equations, two unknowns situation, and we'll find A is equal to 4.44, force of friction is equal to 66.67, and then you find A is equal to R alpha, and you'll find alpha is equal to 1.33. Now the takeaway here that I want you to think about is that I've summed the moments about G is equal to Ig alpha, but there are actually three ways you can do the moment equation, and the other two ways are you can sum moments about A. If you do that, you can use the general equation. Sum of the moments about A is equal to ma of g in the x direction times y bar plus Ig alpha. Remember when we were doing translation, many times Ig alpha went away, but in general plane motion, we have to keep all of the terms in the general moment equation alive. And so I'm going to have a mass times acceleration times y bar plus Ig alpha. And again, when I do that, I can find the alpha with only one step. And I don't even have to solve for the force of friction. However, to find the force of friction, then I have to still do sum of the forces in the x is mass times acceleration. All right. And then the last way to do that is using sum of the moments about A is equal to Ia alpha, and what I'm doing here is using the parallel axis theorem to translate my Ig and my Ig down to point A, and the moment looks like this, and again I can solve for alpha in one step without doing the force equation. Sum of the forces is mass times acceleration equation. Now a takeaway here is that using this process of using the instantaneous center only works, or using the parallel axis theorem only works, and it's only legal if A is an IC. And recall from our work before, where A doesn't slip, it is an instantaneous center. So it works if A is an IC, but it's not legal for any slipping condition. All right, what if the slip condition was not specified, wasn't given in the problem? In this problem, it assumed that it's not slipping, but if that assumption is not given, then we have to determine the slip condition. So there are two ways to determine the slip condition. First is to assume a not slip condition and then confirm it, and then find out if your assumption was correct. In the previous page, we had already solved for the not slip condition. Therefore, we can take our force of friction that we found, which was 66.67, and compare it to our force of friction maximum, which would be mu normal. So that if mu was given as 0.2, I can say that the force of friction of maximum would be mu normal, which is equal to mu mg, which is equal to 196.2. Clearly, 66.7 is less than 196.2, so that says that my assumption was correct. It is not slipping, and so my answers that I got before are correct. However, if mu had been given as 0.05, again, from our calculation, assuming not slip, I have to compare that to the actual force of friction maximum. Force of friction maximum being mu mg, in this case would be 49.05. So where I'm seeing here is that if this is calculated as greater than it can be, this is as big as it can be, then it is not, that my not slipping assumption was invalid. So I have to assume now that it is slipping, and unfortunately I have to rework the problem. I'll have to go back and do all the work again, assuming a slip condition. All right, so that's the first way to determine slipping. Assume it's not slip, and then confirm it. The other way to confirm or to find out whether it's slipping or not is to find the minimum mu to prevent slip. And again, then what we're finding here, or what we remember, is that at that unique spot, the force of friction is equal to mu normal and A equals R alpha at the same time. When I plug those into my two equations, again, I get a two equations, two unknown. I can resolve that and find out the minimum mu to prevent slip is 0.06796. And what it says there is that anything less than, for any mu less than 0.068, it is slipping. For any mu greater than 0.068, it is not slipping. So when I find that, I can use this as my first step, and then I can go back and say if mu is equal to 0.05, then, clearly that's in a slip condition. But if mu is equal to 0.2, in my previous example, then that is not slipping, and I can proceed from there. So then, to recap the assumptions for round and rolling things, if it is not slipping, if I have a round object rolling just without even being pulled, if it's not slipping, I know that V is equal to R omega, A is equal to R alpha, and the force of friction does not equal mu normal. However, if it's slipping, V does not equal to R omega anymore, A does not equal R alpha, and the force of friction does now equal mu normal. If I'm pulling, then these are the force equations and the moment equations that are valid. If I'm pulling, then I got the sum of the forces in the axis, mass times acceleration, is valid for both slipping and not slipping. Some of the moments about G is IG alpha, valid for both slipping and not slipping. Some of the moments about A is equal to IA alpha. Again, this is using the parallel axis theorem, counting A as an instantaneous center. That is only valid if it's not slipping. In other words, if it's slipping, you cannot use the parallel axis theorem and use that. However, you can use some of the moments about A and use the general equation on either a not slipping or a slipping condition. And the difference here is that for not slipping, A is equal to R alpha, and so this term becomes the parallel axis theorem. In the not slip condition, A does not equal R alpha. In the slipping condition, A does not equal R alpha, and so these are two separate terms that have to be evaluated. All right, and then again, the minimum mu to prevent slip is at that unique spot where the force of friction, that's the force of friction, is equal to mu normal and A equals R alpha at the same time.